Welcome to the software engineering class using AI. So, as I've said in the former videos, we are going to learn about the fundamentals of software engineering before we go ahead with the AI aspect of it. So, for this video, we'll be talking about the fundamentals of software engineering, and then we'll be learning how front-end, back-end servers and data work together to build modern software. So this is kind of the fundamental knowledge you have to have um, on software engineering so that you can build a scalable solution using AI tools. So also in this video, you are going to learn the difference between coding and software engineering, because what makes a software is not about the amount of code you write, is about the scalability and then the deliverables. So we are going to learn about all that in this video. So if you are new to this channel, do good to like, share the video, and subscribe to the channel. So a foundation briefing, software engineering fundamentals, how front-end, back-end servers, and data work together to build modern softwares. So what you'll be learning in this video, we will cover foundations, and the foundations will talk about what software engineering is and the SDLC that structures it. And then we'll talk about front end, the interface users see and interact with. And then we'll talk about the back end and servers. That is the logic, infrastructure, and data layer behind the scenes. Then the connecting pieces, APIs, databases, and client server communication. That is the communication between the client side and the server side of the application. Then next and the last one will be craft and discipline. That is testing, security, DevOps, and core engineering principles. So let's just get to the first one, foundations. So under the foundations, we have what is software engineering. Now, software engineering is a disciplined application of engineering principle to design, build, and test and maintain software, turning a problem into a reliable, maintainable system, not just a working code. So software engineering is not just the code you are writing, but then is the engineering principle that that you can use to build, test, and maintain a particular solution called software. So now you are turning a problem into a reliable and maintainable system, not just the code. So with time, that system can be remodeled and then scaled for um, more user or additional features. So before we continue, I'm just going to go through the difference between coding and engineering. Now, coding basically is writing a code that works, um, and then you're solving today's tasks. When you're coding, you're solving a specific task per day, and then coding requires individual effort, but engineering on its end has to do with designing systems that keep working, and then anticipating scale, failure, and changes. Like what I said here, you are building reliable and maintainable system that can be scaled. So when you are engineering, you are considering the scalability of that particular software, the failures that you might encounter, and then what changes can you make to the software in the future. This is what you consider when you are engineering a software. And also, um, when you are coding, you're only considering the task for that particular day. So coding has to do with individual effort, like I said, but engineering is coordinated, reviewed team practices. So it's a coordinated, reviewed team practices. So when you are engineering, you are working with a team. When you're engineering, you're working with the team. And these are the core principles, these are the core factors you need to understand, and you need to know how software engineering works before you introduce AI tools as your team. Because when you are doing software engineering with AI, basically you are no longer working with human team anymore. You're working with team of AI tools to create a scalable, reliable, and maintainable system. So now there are five core disciplines for software engineering, which the first one is requirement. Now you define what you must build. So when you are defining what you are building, like I said in the previous videos, you are um, understanding the problem, you're understanding the system you're about to build. You define it, you understand who it is for, what it is serving for, and why you are building it. You get, so when you understand the requirements, define what you are building, or what must be built, and why you are building it. Then you go over to the next step. You plan the architecture, that is design. You plan the architecture and the system structure, how everything is going to be layered, everything you're working with, how they are going to be arranged. So you plan the architecture just like building a house. The engineers don't just go into building the house, they plan out the architecture of that particular house, and then the architect designs the house and they build with the design. So the same thing is applicable with software engineering. You plan the architecture and then you build the system through that architecture. So the next one here is development. After you've planned your architecture, then you now go in to the major development part. So these first two discipline or core disciplines, you do this by yourself most of the times, or you can require a help of an AI tool to carry out these two first core disciplines. So these two first steps, you can require an AI help, but at this point you need to brainstorm very well. Then when you move to development, this is the place, this is the point or the step where you involve AI tools majorly in the development um, step. So the development just has to do with implementing the solutions now in code. So you use your AI tools, you've understood the system, and then you've designed the architecture. So all you just have to do in this phase is to hand over your architecture and your requirements to the AI tool, and then it builds everything for you, writing everything in code. This is the development stage. After the development stage or the development um, discipline, we go over to the testing. Now you've developed everything, the system should be working. So you test if there are any errors to fix. Like what you said, engineering anticipating scale, failure, and changes. So when you test, you are anticipating failures. You are trying to know where the software is going to fail so that you can fix that and change it. So now, after you've tested and you've approved your test, everything is working, then the next step is the maintenance. So in this maintenance stage, what you have to do is to fix, improve, and evolve over time. So this maintenance is something that is long term. So after you've tested and verified, then you launch the app, then you begin to maintain. Maybe as time goes by, whatever get broken, you fix it, improve, or then maybe if you want to um, adapt new modern technologies, all you have to do is evolve the particular system. So you are also anticipating changes. So we move on to the next one. All right, before we move on to the next one, you find out that understanding these five core disciplines has already given you enough stand to use AI to build your software, even if you've not written a single line of code in your entire life. So you are ready to build a full scalable software when you understand these 5 core principles or stages of software development. So we're going to move on to the next one, which is still under the foundation, the software development life cycle. So we are going to be understanding that a repeatable process that turns an idea into working, maintained software. Most teams cycle through it continually rather than once. So most teams cycle through it continuously rather than just once. So they plan, design, develop, test, deploy, maintain, and then come back again to plan, design, develop, test, deploy, and then maintain. So this is a life cycle. So you start at the planning stage when you gather your requirements, the scope of the work, and then design the architect system and that, and then you write and review the implementation, the coding process of the software. Then you test again, validate functionality and quality. So you test and deploy, release the production environment. So you deploy so that it can be used by your users. Your users can access it. Then you maintain, monitor, fix, and improve. Then if there are new features you want to add to that particular software, you go back to stage one again and then plan, design, develop the new feature, test, deploy it, the upgrade, the upgraded version. Sometimes you can see some software will have new release, upgraded release. So they deployed a new release and then continue to maintain that particular latest version. When there's another upgrade or something to fix, they go back again and plan, design, develop, test, deploy, and maintain. So that is why it is said most teams cycle through it continually rather than just once. So depending on the vision you have for your particular software, so you can cycle these more than 100 times. So that is it. So it can be iterative, not linear. So it can jump, not once it will go through this phase. So modern team use agile scrum. So they repeat this cycle in short sprints of 1 to 4 weeks rather than completing it once, allowing continuous feedback and what improvement. So we're going to go over to the next one. So now you're talking about the front end fundamentals. So you're just going to understand this particular part of it. So what is front end? The client facing side of the application, everything a user sees, touches, and interacts with in a browser or mobile app. Its job is to present information clearly and respond instantly to inputs. So basically, the front end is what the user interacts with, that is the client facing side of the application. So everything the user sees, touches, interacts with within a browser or a mobile application. So the job of the front end is to present information clearly and respond instantly to input. So maybe you are inputting your login details, so it takes those inputs instantly and responds to it. So that is the function of the front end, to present the information of that particular application or website to the user and then get the user response immediately. So there are core building blocks. So you can use HTML to build your front end. So use HTML to structure the pages, contents, and layout skeletons. Then use CSS to style, that is, use it to fix the colors, spacing, typography, responsiveness. So this responsiveness simply means your app will display very, very well in all screen sizes and you can be able to interact with it very efficiently and effectively. So now the JavaScript is another programming language or building block for the front end. So its own is the behavior interactivity, and dynamic updates. So being able to click and then all that are handled by the JavaScript. So popular frameworks and concerns. So here there are frameworks. Frameworks are kind of, in a layman understanding, I would define frameworks as combination of programming language or libraries um, that facilitates the programming of the front end. So what I mean is, so there are frameworks like React now, component-based UI library. So it's made of so many libraries, so you can easily use to develop your front end and then maintain by Meta. So React is maintained by Meta. Now Vue is another framework. It is approachable, incrementally adaptable framework. So you can approach it and then incrementally adapt to this particular framework. Angular is another framework, full-featured framework for large applications. So Angular is mostly used for top complex applications. So now, what are software engineers? What software front-end engineers care about? Now, front-end engineers, what they care about mostly, they are concerned with the usability and accessibility of their design, and then responsive design across devices, like I said, performance and load speed. So the user end must be able to load very fast and um, be efficient when the user is using it. Then consistent UI UX patterns. So the UI UX must be consistent. So if they are using particular theme color set for this page, then the next page should also have that kind of theme color set. So consistent UI UX patterns. So backend fundamentals. So this is the place where it gets kind of complex, but pay rapt attention to understand. So backend fundamentals, what it is. So the server side of an application. So backend is the server side of an application. That is the logic that runs out of the user's site. Now, what the user does not see. As you're looking at YouTube right now, you're watching the video, there are communications from your YouTube app to the servers that you are not seeing. So all those logic that runs outside of the user's site that the user does not see is the backend. It processes requests, applies business rules, talks to databases, and returns results the front end can display. So it talks to the databases, talks to the servers, process requests, and then apply the business rules. Now, YouTube is a business. Maybe YouTube will say, if this particular user that is viewing this video is not up to 18 years, do not display this particular content to the user. So it applies that business rule while you are interacting with it. So it communicates with the databases and return result the front end can display. So it's whatever the back end fits the front end, and the front end will display to the users. Now, common languages are one time. We have the Node.js, we have the Python, we have the Java, we have the Go, we have the Ruby, we have the C# or the .NET. Now, please don't bother yourself with all these frameworks, because you are basically going to be using AI tools to do the job. So you don't really need to understand these very much. You just need to have the fundamental knowledge as you are learning right now, so that you can be able to prompt the AI very well and then be able to make corrections with the AI too. Apart from that, you don't need to know all these programming languages and frameworks. Then the next thing here, what the backend is responsible for. So you have to pay rapt attention, so that when you are talking to your AI tool, you can be able to point out where something went wrong. maybe the front end or in the back end. So what the back end is responsible for is responsible for authentication and authorization. This is for login and security in the application or software you are developing. So it is responsible for authentication and authorization and confirming who a user is and what they can do. So it's also responsible for the business logic. Maybe a user who have not subscribed to the particular um, application should not have these features. So it applies the business logic, applying the rules that define how the product works. So YouTube can say people who have not subscribed to this channel will not have access to this particular video, and that is the business logic that will be applied to YouTube. So moving on, data management. It reads, writes, and validates persistent data. So it reads the database, writes to the database, and validates the database persistently. So the next one is integration, talking to other services, APIs, and systems. So if you have a third-party service, maybe you are trying to use a feature from another application, the database, the backend is responsible to talk to those third-party applications via API or other services. So all these are the communication rules, the APIs, and other services, they communicate together to work in your particular software. Moving on, you will understand how all these factors communicate, the front end, the back end, the servers. So, but then we are going to move on to the next. Connecting the pieces. How front end and back end talk. Every interaction follows the same request response cycle over HTTP. So what is HTTP first of all? HTTP simply means Hypertext Transfer Protocol. So it's a transfer protocol for requests in within the backend. So here is your application. Let's say this entire box is your application right here. So this is your client side browser or app UI. That is the front end. Now your front end make a request to the network layer. The network layer request travels over HTTP or HTTPS. The S here, don't mind this S, it simply means secure. So Hypertext Transfer Protocol, secure. So when you see the S, just know that that particular communication is secured. So when the front end makes a request to the network layer, the network layer talks to the server. Now the server, right here in the server, the backend runs the logic and then queries the database and return response. So this makes request to this, and then this routes that request that it made to the server. Let us say you are requesting for, okay, you opened up an e-commerce app and then you selected some items and added them to cart, and then you want to view your cart, you clicked on the view cart. It makes that request in split seconds. It makes that request through the network layer. The network layer communicates with the server that this particular user is requesting this page. Now, it has sent that request to the server. The server responds back to the network layer with the page that the user requested for, and then the network layer sends back the request to the front end so the user can interact with that particular cart page. Now here, the request response cycle. First of all, the client sends an HTTP request. For example, give me this user's profile. Then the step 2, the server processes it and may query a data to get the user's profile. Then the step 3, the server sends back a response, usually a JSON response. And then step 4, the client updates the UI with the result. So this communication right here is called request response cycle. So moving forward from the front end is the request, and then the server responding back to the front end is called response. So the front end is requesting for resources from the server, which the server might communicate to the database. Okay, there should be another communication right here where the server talks to database or external tools. Then when those send back the request to the server sends it through the network layer. So this is just the route for their communication. This is not a particular um, structure. This is not a particular structure. It's just a route where the communication flow to network layer. So moving on, connecting the pieces now. Pay attention right here. Um, Servers and hosting. A server is a program, often a remote hardware, that listens for request and response with data or services. Now, the servers listens is just like a cloud computer that stays active 24/7 to listen for requests and response to that request with data or services available. It is available continuously, not just while someone is watching. So even if you're offline, servers are available 24/7. Now there are types of servers. There are web servers, serves web pages, and static assets. For example, Jinx and Apache, there are two types of web server. And then there are other servers. Application server runs business logic and dynamic processing. So the application server runs business logic and dynamic processing. Now there are database servers. Database servers stores and manages persistent data. So database server is responsible for holding all the data that are required for that particular application to work. On-premises versus cloud. Now, on-prem or on-premises is a company owns and maintains physical servers. So a company owns and maintains physical servers. That is the one you can see. And then the cloud capacity is rented from providers like AWS, Azure, or Google Cloud, scaled on demand. So these are servers that are held up in the cloud where you can rent from AWS, Azure, or Google Cloud. Now, uptime, you usually hear this when you are dealing with servers. Uptime simply means percentage of time a service is available and running. So, when you are choosing a server, look at the uptime. What percentage of time will this server be available and running? So load balancing is spreading traffic across multiple servers. So instead of weighing down a particular server, you spread the traffic across multiple servers so that your application can be fast when running. Now scaling is the vertical, a bigger server, horizontal, more servers. So vertical scaling is getting a bigger server, just one server that is bigger. But then horizontal scaling is getting multiple servers to do the job for the application. So you need to consider all these when getting your server for your application. AI will not get your servers for you, but it can suggest the best for you. So then moving on, connecting the pieces again. Now we are at another stage of connecting the pieces. Now, listen very carefully. Databases, what are databases? They are where data lives. We have talked about that. Now we have the SQL relational database. It is a structured data in table. It's structured data in table with fixed schemas and relationship between them, queried with SQL. For example, PostgreSQL, MySQL, SQL Server. It is best for structured data with clear relationships, transactions, um, financial records. So most times, people go for Postgres because it is very best for structured and clear data. So if you are building a fintech application, you have to go for Postgres. Or if you are building an e-commerce app, you have to go for Postgres because your data is structured with clear relationship, transaction, and financial record. Now, NoSQL is a non-relational database. It deals with flexible data models, documents, key value pairs, or graphs without a fixed schema, built for scale and speed. So the NoSQL is built for scale and speed, like the MongoDB, the Redis, the Cassandra, they are built for scale and speed. So it's actually good, best for storing key value pairs, and also best for rapidly changing data, so data that can change continuously, and good for checking, and then huge volume slash velocity workloads. So if you are dealing with huge volume and large velocity workloads, you need to consider using the NoSQL, one of the NoSQLs. You can create an account on MongoDB or Redis or Cassandra and then set up your cluster over there. Then one more term you need to learn is the CRUD. So the CRUD is a form basic operation on data. So what it actually stands for is create, read, update, and delete. So this CRUD, call it the CRUD, stands for create, read, update, and delete. So the create adds new record, and then the read retrieve existing data, update, modify existing records, and then delete or remove records. So basically, um, they are self-explanatory. So create, read, update, and delete. So these are the four basic operations on data. Moving forward, we'll be talking about APIs, the contract between systems. So API is a very common concept in modern application. So be attentive so you can grab it. API is the contract between systems, so it's kind of the communication flow also. An API, application programming interface, defines how the front end, back end, and other services request and exchange data. A shared set of rules both sides agree to follow. So this is kind of a contract between the systems. So both sides, the application side agrees to follow this set of rules, and then the server side agrees to follow that particular set of rules. Now, common HTTP method, or we call it REST, get, post, put, and delete. So the get retrieves data just like the R for CRUD. So the get retrieves data through the API. So you can make a get request through the API. Something like this, get user and 42. So this is kind of a get request when you're communicating with APIs. So now the post request looks like this. Now the post is for creating new data, and it looks like this, something like this when you are trying to create a new data through the API. Now, the put means update existing data. So you are updating or modifying existing data. And then the delete stands for removing, so you can make a delete request over the API with something like this. Now, data transfers data travels as JSON. So REST APIs typically exchange data as JSON, that is JavaScript object notation. So that is the full meaning of JSON, JavaScript object notation, a lightweight, human readable text format both front end and back end can pass. So for both the front end and back end can pass the JSON easily. So JSON files or JSON files always look something like this. So it can be readable. Human can read it. It's a lightweight human readable text format. So it's readable. You can look at it and easily understand what it stands for. So this is kind of item 42. Then the name Ada and then role engineer. So you understand what this particular file is trying to read or is trying to pass. So let's move forward. So like I said, API is like the contract between the systems. So the API is like the set of rules. Okay, you need this, you have to follow this particular set of rules, and that is what the API stands for, Application Programming Interface. So moving on, we're talking about version control and collaboration. So version control and collaboration, mostly we deal with Git, that is Git tracks every changes to a code base over time, letting many engineers work on the same product without overwriting each other's work. So you can work on your let me say there are a team of engineers and there is a shared task. You say engineer A work on the front end, engineer B work on the back end, and then you take care of the API layers and then all that. So each of these particular engineers work on their own aspects of the project without overwriting any person's work. Yes, without overriding each other's work. So you work on your own and then I work on my own. At the end of the day, Git tracks every changes together and brings up the updated version. So that is why we use Git for version control and collaboration. So in Git, when using Git, you hear most times about repositories. So repository is the full project including its entire history and changes. So that is what repositories means. Then next thing we hear is about commit. They will say, have you committed the changes? So commit means a set snapshot of changes with a message describing what that change is actually about. So let's say you are changing the hero section of a website from design A to design B. So when you are committing design B, you can write a describing message into your commit saying updating front end hero section to design B, and then it saves that up. Then you hear mostly about branches, very important. So branch is an independent line of work isolated from the main code base. So maybe if you want to test out something or there is a change that you're not sure of, you can push that particular change to a separate branch that is isolated from the main code base so that you don't interrupt the already working system. So then the next one is the pull request. A pull request is a proposal to match one branch change. So when you have like the example I used, you are not sure of the changes you made and you don't want it to spoil the already working system. So you committed or you pushed those changes to a separate branch. Now, when you are finished testing those changes and then you are sure of it and you want to merge it together, so you can make a pull request. It merged the two branch changes together. Now, opened for review. So when you merge it together and then it can also be reviewed. Now, typical workflow, you create a branch, commit the changes, open a pull request, then teammates review, and then merge into one branch before deploying. So you create a branch, commit changes, open a pull request, then your teammates review that particular pull request, and then you can be able to merge the branch and deploy. So moving on to the next one, um, craft and discipline, software architecture patterns. So this is how system software architecture patterns, how a system's pieces are organized, shaped, how easily it can scale, deploy, and evolve. So we have the monolith, one unified code base and deployment, simple to build and deploy early, but harder to scale. So the monolith is just like you have one unified code base. You did not split any work. Everything is just there together. You did not split any work. You did not split the services. So it is harder to scale specific part of it. So it is harder to scale. Then we have the microservices. So it is independent services per business function. So you can scale and deploy pieces separately. So um, you kind of made the independent um, parts of the business, kind of programmed it separately, independently, and then all are working together to produce that particular application. So that is what this microservices is all about. So you program and deploy them separately. But then it has its cons. It is more operational complexity. So it has more operational complexity. And then there are serverless architecture patterns. So could run on provider managed functions. So no server, no server management, pay per use. So you don't manage the server, you pay per use. So you have less control of your server and potential cold starts. So you can wake up sometimes and then your you need to cold start your workflow again. So we move on. This particular is not too much to learn about in this particular software engineering using AI course. So you just have to get the idea. So now we move on. Craft and discipline also, testing and quality assurance. So this is a very important part of this. So when you have built your software with AI tools, you have to test. Very, very important. You have to test and ensure that what was produced for you is up to the quality you you needed, up to the quality that can be sold out to users. You understand? You have to make sure that it is up to the market standard so that you don't build something that users will not appreciate. You understand? Now, testing and quality assurance again. Testing catches problems before users do. So it is very, very important to test your software so that you can catch problems before your users do. Now, for applications that are built with AI, there is a high percentage rate that you will encounter problem with that software in the future. So when you test, you get the problems first before your users do. The earlier a bug is found, the cheaper it is to fix. So it is better you find out a bug at the early stage, even at the development stage. You find out the bug and fix it than when you now have millions of users or hundreds of users even, and then you find out that it becomes more difficult to fix because when you have more users, you'll be considering how do you fix this particular bug without interrupting their flow using the particular application. So we have um, stages of testing. You have the end-to-end, you have the integration, and they have the unit testing. So you test per unit, then move over to testing per integration, then move over end-to-end. So what it means is you develop a particular unit, you test that particular unit and ensure that it is working, and then you develop another, you test and ensure it is working. Now, when you integrate those units together to become a system, you test that particular integration and ensure that each integrations are working. Now, when you are done integrating everything, you test the entire application from end to end. You run it like you are an actual user. This helps you catch hidden bugs. What each layer actually verifies. So the unit test individual functions is isolated. So you test per individual function of the features or units of your application. So integration test, multiple components working together. So like I said, you test multiple components working together. End to end, full user flow through the whole system. So you test like you're an actual user. Unit tests are fast and numerous. End to end tests are fewer and slower, but check the whole system. So my advice is when you build a particular system, when you are done building a particular unit, you test that unit, and then after your integration, you also test, and then after integrating everything, you after you are done building the entire system, you test from end to end. It helps you even get clearer view on what can be upgraded, what can be changed in the future. A bug caught by a unit test costs minutes to fix. The same bug found by a user in production can cost hours of debugging. So like I said, it is better to catch a bug even when you are doing your unit test. The damage, reputation, and lost revenue. So this is what is going to cost you: damage, reputation, and lost revenue is what is going to cost you when a user catches a bug. So automated tests also let engineers change code confidently, knowing existing behavior is protected. So it is better to test when you are still building. It's better to test. In fact, test at all these stages. That is my advice. That is the way I go about it. I give time to testing more than development, because at the end of the day, you wouldn't want to build what your users will end up rejecting. So, still under craft and discipline, we have the security fundamentals. Security is built in from the start, not added afterward. Every layer of the stack needs it. So every layer of your stack needs security. You need to do security audit at every stack of your development layers. So the authentication versus the authorization. Authentication confirms who you are, that is during the login. Now authorization determines what you are allowed to do once verified. So for some applications that have different user types, when the authentication verifies your user type, now it is the authorization layer that now decides what will be accessible to you in that particular user type. Yeah, so authentication is different from authorization. Authentication has to do with verifying who you are, and authorization is giving you access to the resources. So when it verifies your user type, then authorization checks what resource is available for your user type. And then the next one is encryption in transit. So HTTPS/TLS scrambles data traveling between client and server, so it can't be read if interpreted. So what the HTTPS and the TLS does is to scramble data that are traveling between the client and the server so that it can't be read. So there is this attack that is called the spoofing attack. So the user or the attacker intercepts this particular interaction between your server side, your client side and your server side, and then interprets what those data is. Let's say now you making a bank transfer. Now when that transfer is sent after putting your PIN, that particular attacker, when he spoofs into your network, the network of that application, can reroute that particular transfer to a separate account, because when he reads the communication, when he reads that particular data traveling, he understands it, and then he have a method of rerouting that particular transfer to a separate bank account. So that is the spoofing attack, or they can read confidential information. So encryption is important. Common vulnerabilities for applications. Issues like injection attacks and cross-site scripting arise when input isn't properly validated and sanitized. So this particular vulnerability, cross-site scripting, is very common because inputs are not validated. So there is every necessary you need to validate the inputs coming into your app so that you won't be vulnerable for cross-site scripting. So least privilege. Every user and service should have only the access it needs to do its job, not more. So don't give every user all the rights. Yes, don't give them access to every resources available in your app. So you just give them the one that is needed to do the job they have on that particular app and nothing more. So if it's an e-commerce website, a buyer should only be given access to buyer's resources. You shouldn't say, okay, the buyer should also be able to have the sellers be able to sell, because with that you are increasing vulnerability in your site. So a buyer remains a buyer. If he wants to sell, he should create a seller's account. So a buyer account should not be able to sell. So that is what least privilege actually means. So moving forward, still under craft and discipline, we have the subtopic DevOps and the CI/CD. So DevOps optimize the streamlines how code moves from a developer's machine into production safely and often. So you write your code, engineer writes and commits, then code compiled and packaged, tests, automated test runs, deployed, released to production, and then monitored. Performance and error are tracked when it is monitored. So the key concepts, like we mentioned here, the CI/CD. CI means continuous integration. So merge code changes frequently, testing automatically each time you merge code frequently. And then the CD means continuous development, automatically ship verified changes to users. So when this particular change is verified, it is automatically shipped to the users for the continuous development. But then the continuous integration merge code changes before verifying it. It merged the code changes first before testing and then um, deploying it. But then the continuous development automatically ship verified changes to users first. So after you code and then you build, so you send for test and then it deploys when it starts. So let's move on. craft and discipline also. Core engineering principles. A hand of a handful of enduring ideas guide good software design, regardless of language or framework. So we have the dry concept, which is don't repeat yourself. So, like we said, core engineering is a handful of enduring ideas guide good software engineers, regardless of language or framework. So, when you have a handful of ideas, you work with that and run with that. So, don't repeat yourself. Every piece of knowledge should have one clear source of truth. So do not try to recycle so many knowledge. Just hold on to what you are holding and build on it. Now we have the KISS concept also, which is keep it simple. This is the most common concept. So just keep your flow simple. This is common for vibe coders because you can easily build with AI. You want to pack the entire feature that you can imagine into one software. Forgetting about this key principle, keep it simple. When it becomes complex, you lose users. But when it becomes simple, you gain users. So favor the simplest design that solves the problem. So just look for that particular simple concept that solves that particular problem and stick to it. Do not jam pack so many um, features into one software. Just keep this design simple, keep the application simple. Separation of concerns, divide responsibility. Very, very important. Each part of a system should do one job well. So each part of the system should have one job it is doing and it should be able to do it well. So if you have a blog section, it should be able to do the blogging very, very well. If you have the advert section, the advert section should be used for adverts and it should carry out the job very, very well. So divide responsibility when building your particular software. So we have the solid, which is 5-up design rule, which means guidelines for maintenance, extensible object-oriented code. So you have to follow the 5 OOP design rules. Yeah. So this is object-oriented programming. So guidelines for maintainable, extensible, object-oriented code. So we can actually research on that to know more on it. So why principles over rules? These ideas won't tell you exactly what to build, yes, but they consistently push design towards code that is easier to read, test, and change later. So these principles keep you towards code that are easier to build, read, and what change later. Key takeaways. So it all fits together. The front end presents information and captures input. The back end applies logic and manages data. Servers keep application running and reachable. The client server model structures every interaction. API, APIs and databases are the connective tissues that let system exchange the persist information. So API and database allows the connectivity and let the system exchange and persist information. So testing, security, version control, and DevOps are what turn working code into reliable software. So when you test, apply security, apply version control, and then you can now deploy on the DevOps. Your application comes to life. So these are what make your working code reliable software. So keeping these concepts in mind, you can just grab this last part and keep it in mind. I'll just recap it one more time. So this is basically what you need to understand before building a software using AI. In the next video, we will talk about using AI to implement. So let me recap one more time. The front end presents information and captures input. The back end applies logic and manages data. So the front end, what the user sees, presents information, what the user sees, and captures the user's input and takes it to the back end, while the back end applies the logic and then manages data depending on the request that the user is making. Now, the servers keep the application running and reachable. So the servers are always online, 247, are always available, they are always reachable so that the application can be reached. So when your server is down, your application is automatically shut down. So the client server model structures every interaction. So this client server model structures the interaction between the client side and the server side. So APIs and database are the connective tissues that let systems exchange and persist information. So APIs, like we said, these are the connecting tissues that connects the front end to the back end, from the back end to the DevOps. So it connects the entire system. APIs and database connects the entire system for the system to exchange and persist information. Testing, you test out for errors. Security, you make sure that your software is not vulnerable and your users are safe. So version control, you manage your updates, your fixes, and all that. So the DevOps, you deploy and host where your application comes to life. So these are what turns working code into reliable softwares. Thank you very much for watching this video. Once again, like, share the video and subscribe to the channel so that we can um, reach out to as many as that need this information. Thank you once again. Thank you for watching.